everything is very important. Science is an ecosystem, I like to often say. In fact, science and the technology that it spawns, uh, the whole thing is like the Amazon rainforest or something. It needs a lot of different kinds of diversity of species and flora and fauna to make it rich and enable new things to come out.
Hello and welcome back to The Frontier, a physics series where we have conversations with esteemed researchers in the domain of physics about their fields, why they do what they do, and their journey with science. Today we have Professor Rajesh Gopakumar with us. He's a theoretical physicist and the director of the International Center for Theoretical Sciences in Bangalore. Professor Gopakumar is a very accomplished string theorist, and his research has been highly influential in the fields he's worked on. His work encompasses various domains within string theory and quantum field theory. He's well known for his contributions in topics like N-gauge theories, non-commutative field theories, and topological string theory. He's also worked on attempts to derive the ADS-CFT correspondence, and more recently, conformal bootstraps, which, if I understand correctly, are mathematical models to constrain and solve conformal field theories. Professor Gopakumar did his master's from IIT Kanpur, following which he joined Princeton University for his PhD under the supervision of David Gross, Nobel laureate. Before returning to India to teach at the Harish Chandra Institute, he was a research associate at Harvard University. He was also a long-term visiting fellow at the Institute of Advanced Study in Princeton. Professor, thank you so much for coming on.
My pleasure, and I'm happy to join you and the audience today for this podcast.
Great. So let's dive into it. So I want to ask you initially questions that we ask all the physicists that we have here, beginning with why you chose physics.
Okay, yeah. So it is in, at least in India, it is considered a bit of an unconventional choice, and it certainly was when I studied went for college. Perhaps now it's a little better, and we can touch upon that later. But I think I was always interested in science and mathematics, and I used to have a group of friends at school. We used to always chat about new things, exciting things in science, which we learned about or read about, and which was not necessarily in our school. What was being taught at school. I remember having. I think my I when I was in class 7 or 8 and so on, I used to have these two parallel tracks. I was interested in mathematics, but I was also interested in chemistry and try to sort of gather together little bits of chemicals and just play around. But then I think it was through chemistry, and then when I got to know that about the atomic structure and the rules of quantum mechanics that really determine what the atom is like and the structure of the atom. So that made me want to learn what this mysterious quantum mechanics was. And at the same time, I was also interested in mathematics, and it's sort of very powerful. Both its the sort of sense of elegance and beauty it had, and of course the major role that it plays in physics. I think by the time I was in high school, I was very clear I wanted to study one or the other of mathematics or physics, and preferably something which sort of had both of them in some good measure. Which is why I guess I have gravitated more or less to something which is on the more mathematical end of physics. But the idea of some of the conventional vocational sort of things like the IITs for engineering and so on never really appealed to me. I couldn't see myself doing that, and I was more inclined towards a lifetime of immersion in mathematics and physics. So I think that's how it came about. And yeah, it was not easy to convince many people, but I think my parents came around to the idea at some point, and yeah, and then I think things worked out.
Okay. So around when did you decide you would want to enter high energy physics?
Yeah, so I guess when one when one is studying things like quantum mechanics and so on and so forth, when one is sort of exposed to physics, at least in the way I was, and probably largely people still are, I was always I mean, one heard a lot more about the laws that govern the basic particles, the fundamental interactions. And of course, I was also interested in cosmology and the universe. In fact, it's interesting because of this year's Nobel Prize, when I was in class 11, I think Roger Penrose came to Kolkata, where I was a student, and he gave a talk at the planetarium. So this was probably 1985 or 86. And he gave a talk on black holes at the planetarium in Calcutta, which I attended. And I even remember asking him a question then. But it was sort of, but I had read a little bit about Stephen Hawking and Penrose and so on, their work on the quantum properties of black holes, etc. So that was something that also fascinated me. And there was the TV series by Carl Sagan on Cosmos, which I think also around the same time in my high school era that also played a major role in sort of giving me the impression that these were some of the frontier areas in physics. I guess as you learn more of that when you go to college and you get exposed to other areas, you realize there's more to physics than just that, than just particle physics or cosmology and astrophysics. But you realize that there are many frontiers in physics. It's not only in the very small or the very large, but it's also in the very complex and the very diverse aspects, the very chaotic aspects, and so on. But I think, nevertheless, I think with the kind of bent of mind I had, which was more mathematical, I think it was perhaps more natural that I went towards the areas of high energy physics and quantum field theory and string theory, which I'm currently working on. So I guess there's some aspect of that. I think, mathematical thinking, the importance of mathematics grows in some of these areas relative to some of the others. And I think a combination of mathematical and physical intuition is what often drives progress in these areas, whereas in several other frontier fields of physics, which are also very exciting, very often it is more of a stronger physical intuition and less of a mathematical intuition. So I think this, so one has to find one's right balance where one's strengths are kind of are able to have the most impact. And I think that is what determined my final choice of the area.
I see. So it does seem like you entered it with interest that you had even before you were entering it. And so looking back, how would you say that interest that got you into it has evolved? What is one thing that you've grown to appreciate more about the fields that you've worked in?
Yeah, no, so of course, when one is a school student, of course, one doesn't even really know what research means, and at least I didn't. And even when one is in college, one gets a glimpse through some of our very good teachers. We got a glimpse of what research meant in many of these areas, and what so I think the evolution of one's thinking about the kind of problems one tackles, and what are the tools and the thinking that you need, the creativity you need to tackle different kinds of problems. I think that's something you appreciate more and more as you evolve through your student years and your research career years. I think what I said earlier about different fields requiring different strengths, there are lots of fields now which require heavy computational strengths. There are fields which require, I mean, if you go into experimental physics, it requires you to have a feel with your hands and how to sort of improvise and think of clever ways in which you can measure things and do things and get around various obstacles. If you are doing even theoretical work in certain areas like condensed matter physics or complex systems and so on, you have to, in addition to various other skills, you need certain physical intuition. You have to build a certain physical intuition of how such complex systems might be behaving, which is not often very easy to capture mathematically, but is a kind of a good intuition that good physicists develop over time. I mean, there are famous examples of people like Philip Anderson, who passed away recently, who was sort of the, in some sense, the grand old man of condensed matter physics and complex systems. He had this remarkable insight, in which required him to synthesize a lot of knowledge, information, physics, and so on, to have a picture in his mind of how complex systems in nature work. And there are such a diversity of them, and many of these have not yet been figured out. So different fields, what I mean to say is different fields require these different strengths. And what I hadn't fully appreciated that landscape of different talents one needs, and something like string theory, you have to you need, of course, a strong mathematical grounding, but together with a certain amount of physical insight of a certain kind, sort of a more structural understanding of how theories work and how things fit together, and the kind of, it's like a jigsaw puzzle, how things are kind of, all the different moving parts, how they kind of come together. So you need to have these different strengths, and I guess, I mean, I was sort of fortunate to probably end up working in an area which I think is where I think I can contribute most in terms of my strength. I should say another thing, that one gets a little wide-eyed and starry-eyed, I should say, about fields like string theory and cosmology and the fundamental questions. But I should also sort of add a cautionary note that very often in these fields, progress is very slow in some sense, because one is firstly building on a large edifice, and it is you have a theoretical structure which you're trying to push ahead without disturbing everything that has been built. The structure of physics, or the structure of the theoretical frameworks underlying physics in these areas is very delicately balanced and put together. You can't just do violence to some part without the whole thing falling apart. So to be able to make non-trivial progress in these areas, firstly, you have to do it without too much experimental guidance, which I think previous generations had a lot more direct, even the generation of my advisor and so on. I think their theories and so on were informed a lot by experimental results, and but in the areas of high energy physics, new experimental results, things which sort of push you to the next frontier, these have not been coming that easily. So this is something, of course, which I wouldn't have known at the time, and it was probably not even true at the time when I was a student, but it is true now, maybe 35 years later. But and that's something I think people should keep in mind. And even foundational work like Roger Penrose's, I think got recognized in some sense. I mean, it was recognized, of course, in the community, but it's sort of, you can see direct observational evidence of black holes now in some very clear-cut ways, maybe 40, 50 years after after they were believed to be ubiquitous, after the work of Penrose and others showed that they must exist must be very common in the universe. Of course, black holes had been predicted another half a century earlier, but I think till then they were considered much more speculative, and it's only in the last half a century or so that they have been really believed and experimentally found to be very common in nature. So time scales are long for discoveries, both theoretical and experimental, in these areas. So that's something I think one realizes after, and one realizes now in hindsight. So I think the preconceived notions a lot of people have is that, oh, this X field is fundamental and that those are less fundamental and less interesting, therefore, and so on. I think these are kind of a little bit silly preconceptions. I think the physics advances on many frontiers, and the laws of complex systems are equally difficult to disentangle and play a fundamental role in our understanding of nature. So I think one should not view things too much in terms of some kind of a hierarchy of disciplines or sub-disciplines or areas. I think that's the notion that is sometimes comes students get ingrained with, but I think it's good to sort of shed that.
Okay. So I do want to pick out one thing that you just mentioned about how now experiments don't inform as much as probably the previous generation would. And so
in the areas of string
yeah,
theory
in the areas, yeah. And so
not
yeah. And so can you maybe talk about one or two things, kind of experiments that people are looking to do to say verify some of the work that's being done in theory? What is the
So
hope for the experiments?
yeah, so traditionally, of course, the fundamental the laws of nature in terms of the fundamental interactions. I think people have progressed in understanding that through particle accelerators and so on. And this is what the big accelerator at CERN was very successful in discovering, the Higgs boson, but which was a prediction from over 50 years ago. But it was successful in verifying that prediction, but it has so far not provided any new evidence of physics beyond the so-called standard model of particle physics, which was in place about 50 years ago. So we have not had much success in pushing things there. It might change. I mean, then maybe additional powerful accelerators that are there that are being planned in the next couple of decades. These might uncover something completely unexpected, because so far things have been, physicists don't like it when their experiments are too well fitting to theory, because they want to obviously go ahead and find something that doesn't fit, and therefore gives you a clue to what lies ahead. And so, but unfortunately, that has not been the case, and experiments have been beautifully fitting theory. Though there are reasons to believe that something has to give at some point. And there are puzzles like the origin of dark matter and dark energy and so on, which we have to find the experimental clues for. So, so in some sense, the frontier of physics in the very small actually has moved to the frontier at the very large scale. So what I mean to say is that the new exciting experimental results have been coming in cosmology, which has become, when I was a student, I read some of Narliker's books on cosmology and so on, and which were very nice and this thing, but the experimental evidence was very scanty. And this is why people couldn't even really distinguish between multiple theories, etc. That situation has just changed drastically in the last 50 years. And now we have we have precision cosmology. And so the experimental results there firstly indicated that there was dark energy, which people hadn't suspected really to be there at the level that people have found it. Similarly, dark matter has become a very, people have realized that you have to figure out what are the constituents of dark matter. These are some of the areas where I think experimental results in the coming decades. There are multiple experiments going on, even terrestrial experiments, space-based telescope experiments, things for dark matter, things for looking at the early history of the universe. All these are likely to give more clues to to some of the for some of the theories that are being developed. And at the same time, new things like gravitational wave detectors have also opened up other new horizon, a whole new way of looking at the new window into the universe. Perhaps black holes, which are sort of very puzzling objects from the point of view of quantum gravity, a quantum theory of gravity, they are now things we can try to understand over the next half century. I think we'll have understood many of their properties much better. Right now, we are still probing the classical properties of black holes as proposed by Einstein and so on and so forth until Penrose. But the sort of quantum properties that Hawking and others discovered, I think I think the next 50 years we probably might be able to learn more, and that will shed light also on theories of quantum gravity, which once again also play a role in the very early universe in the Big Bang. So both of these, from both of these directions, both from the early universe and cosmology, we can learn, I think, about quantum gravity, dark energy, dark matter, and from black holes and through gravitational wave detectors, we can learn more about, I think, the properties of black holes. And while there will be the traditional high energy particle physics accelerators, which hopefully will also sort of turn the corner at some point and see amazing things come out of that.
So yeah, I did ask the question about experiment, and I just realized that you said something in the beginning about how delicately things are put together in the framework for if we come back
Yes.
to the theories of the very small. And so you've said that up until now, experiments are fitting beautifully with the theory, but when they don't, what does that mean for the theory? Does it mean that years of decades of work would be rendered wrong, or what? Like, what does that mean then?
Yeah, no, that's a good question, because the way in which I think there is often insufficient appreciation of this, the way theories develop. I mean, when Newton discovered the laws of gravity and described the planets and Halley's comet and what have you, very remarkably using his laws. They were very successful. They fitted everything that people had measured for 3 centuries. It was fitting. But then what Einstein realized was that Newton's laws have limitations, and some of which Newton had himself actually realized, but but nevertheless, he had that was the framework he was working in, and it was successful. So he went ahead with that. But Einstein managed to overcome those limitations and gave a sort of quite a radically different picture of gravity. But the remarkable thing is, and this is what is, I think, less appreciated, is that the Einstein's theory reduces in a certain appropriate limit to the Newtonian theory of gravity. And therefore, it does not invalidate anything that Newton says. It just says that Einstein's theory is a more complete description, a more comprehensive description, which you can use to describe a wider range of phenomena. But if things are if you are looking only at a certain corner of phenomena, Newton's laws are adequate because in that corner, the bigger framework reduces to the smaller one. And it's the same when classical mechanics was replaced by quantum mechanics and so on. So whenever a theory grows, it sort of has to preserve the theory that's already working very well. It has to sort of encompass that, but grow beyond it, extend its validity in an experimental sense, just like Newton's theory breaks down when velocities are approaching the speed of light, or densities are going towards that of a neutron star or something. So Newton's theory very much breaks down, and we know that Einstein's theory does a much better job there. Einstein's theory would also break down when you have to take into account quantum effects. That would come in at a much different scale, different length scale, time scale, etc. So you have this sort of nested structure of theories, each of which is sort of wider in scope than the previous one, and but encompasses the previous one or reduces the previous one, reduces to the previous one in an appropriate mathematically defined limit. So this is what so when one finds a theory beyond the standard model, it would reduce to the standard model in an appropriate limit, but it would sort of not jeopardize any of the findings of the standard model, but will be a consistent structure that enlarges it. And so that's what it would be like, and that's what it has always been for physical theories as they've sort of been generalized.
Yeah. So we do have evidence for the standard model, right? But what we're looking for is evidence from all of the theories that we've made about physics beyond the standard model. Evidence for those kinds of things are not there yet. And so
Yes.
it's like the theory is kind of ahead of the experiment right now. And so
Yeah.
if I do ask the same question, but I limit it to just theories beyond the standard model, what does it mean for them? It will of course be incremental, it will be built upon the standard model. But does that mean that, say, if we didn't have experimental access to those domains for like 2 or 3 decades, then all of the work that's been done in those 2 or 3 decades, only a little like slice of it will be correct? Or does that mean that, you know,
For all the theories beyond the standard model?
yes,
So typically theories that extend other theories, well, I mean, there are various ways in which theories can be extended, but one way, it's a sort of a parametric extension, meaning there's a parameter which in some limit, when one becomes very small, reduces to the other theory. So you can extend the standard model in multiple ways within, at least within the broad framework of what is called quantum field theory. There are multiple ways by introducing different particles, different additional stuff. You can extend in ways, but they're all controlled by certain parameters like the masses of those particles or their strength of their interactions with the existing particles. So what experiments always provide are sort of upper bounds on those things. So it says that, or lower bounds, depending on upper bounds on the strength of interaction, or lower bounds on the masses or something like that. It says that the masses can be only higher than this, or the interactions must be weaker than this. So you keep pushing the parameter range of these theories, and at some point they become unnaturally tuned, so to say. I mean, they don't, the range of parameters to which they're pushed sort of becomes meaningless, or it's sort of something else anyway would have to come in. And so that's when you kind of when you sort of eliminate those theories. But it's true that so we don't know, of course, what form the new theory might take. It might be one of the existing candidates that are there, but there are many of them. And supposing one is picked out, the others will, of course, will only play a historical role as a proposal. But then that's how it was even for the standard model. At that time, there were multiple other proposals as well, but it was only the standard model that really, with its particular set of particles and interactions, and so to say, which survived. And there are others which are historical, I mean, proposed as models, which didn't capture all the experiments. So that's how it will be for for the majority of the theories that we have right now. Or it could be that there is something that we haven't thought of yet, and it's not just one of the current existing ones that will be the right one, but something else which we haven't had the imagination yet to sort of come up with. And yeah, so that is, of course, the challenge and the exciting thing about research at the frontier.
Okay, so on that note, I do want to. I'm curious about this. What you think about theoretical physics research as opposed to other scientific fields, and even if we consider research in math, would you say that these kinds of fields, this kind of work in theory leans more towards how work in math is done, in that you have a few axioms and then under that kind of framework you perform calculations, or is it similar to how like the scientific method is followed in other fields of science, wherein you do have experiments, but in this case we don't have access to experimental data yet?
Yeah, so no, I must say that even though physicists use a lot of mathematics and sophisticated mathematics, or even come up with their own mathematics, uh, their approach is often orthogonal to that of a mathematician. Yeah, I have rarely met a physicist, primarily a person who is primarily a physicist, who has proceeded on an axiomatic approach. There are some sort of old school mathematical physicists who do that, but very few. I mean, it has traditionally not been a very fruitful way to proceed. But instead, what you use is a mathematical framework, and the way you try to generalize existing frameworks is, as I said earlier, and which you came back to, this thing of this delicately put together. So to kind of generalize something which is delicately put together, the more and more it's like you've built a sort of a big mechanical Lego model or something like that, and you built a very complicated thing with a lot of moving parts, and now you want to extend it to do something else. It's not going to be very easy. You can't just randomly put something there without the whole thing getting jammed or falling apart. So you have to know how to extend it, and often the mathematical structure of the framework suggests to you how it can be extended, and because there's an inner coherence, a mathematical coherence and mathematical consistency often guides you, and that's what in string theory, in the absence of experiment, has been a guiding principle. And as the coherence and consistency are very strong requirements. It's much stronger than one thinks, especially for these things. There are very few things you can actually tinker around with, and even though you are, it's I mean, you mentioned the classic scientific method of theory then being tested by experiments. Of course, I think that's how every practicing physicist or scientist, whether it's a string theorist or a condensed matter physicist or an astrophysicist, will approach things. In the absence of direct, immediate experimental tests, there are still many checks, and you can try to sort of stress test it, so to say, with in many ways to make sure that the structure is robust and and you try to, of course, everyone is free to try to extend in multiple ways, but very often you see that many of these things end up roughly in the same framework. And one of the recent developments in string theory, I mean, the last couple of decades, has been this ADS-CFT correspondence that you mentioned, and that is something that relates a pre-existing framework of general relativity, the Einstein's theory of gravity, to another framework, quantum field theory, both of which existed for are now almost a century old, and they existed prior to string theory. But actually, string theory predicts some remarkable relations between these two, which is something you can actually experimentally verify within these frameworks, which are themselves experimentally validated, and see that there is this thing. So string theory, so these are the sort of the consistency, the ability to reproduce things like the Hawking entropy. These are the things that string theorists hold on to in the absence of experimental this thing as very non-trivial checks that they are on the right track. But of course, in the end, you can still be fooled, and experiments are this thing. But as I said, the time scales have grown longer, and this is the reality of the progress in this area. So you have to work with what you have, and I think this in mathematical consistency and theoretical stability of these frameworks that one is developing is a very robust criteria.
So why is it that you can be fooled if there is this kind of inherent mathematical consistency that our techniques have, and we are trying to operate within a well put together framework? Where is it that we sort of go wrong when it comes to actually describing reality? If the
No,
experiment has to be
it's just that, I mean, it's our conceit that nature will follow what we have the imagination to think of. Nature might be smarter than us or more creative in some ways. There are probably mathematical structures which we haven't yet dreamt of or imagined, which would be ways of extending it. So it could be that you're looking under the lamppost, or it could be that maybe yes. So this is why I say one should be always cognizant of the fact that you might be fooling oneself. But in the absence of evidence to the contrary, I think the fruitful attitude is to sort of progress with what you have, and of course be rigorous in your examination of your assumptions and the things that go into things. Be very self-critical, self-aware.
I see. So if we come back to your college experiences, you did mention that you got a glimpse of how actual research is conducted. But what was your very first experience with doing research, with being part of like a team doing research, say, or just hands-on experience with actual research?
Yeah, well, I mean, in some sense, I guess it's a gradual sort of an evolution. I remember when I was in eighth standard, I was trying to trisect an angle. I was with a ruler and compass and trying to do things. I mean, of course, that's impossible. But I didn't want to take it on fact because at that time I didn't understand the proof of why it's impossible. But I didn't. So and then various other little things. So each little thing that you discover for yourself or play around with yourself is a form of research, however humble and however maybe you're just reinventing the wheel of from long ago. I remember I was very thrilled when I discovered something that I think people knew 2000 years ago, that all the Pythagorean triples you can characterize, all the numbers that obey, integers that obey square plus b square is c square, you can characterize in terms of two sets of integers, m and n. So you discover all these things on your own, but you feel, yeah, you've sort of done research. So I think I used to like playing around and had these little things to sort of go with. But in college, yeah, I mean, I think our teachers gave us often very interesting, challenging problems. It didn't often lead to anything which, at least anything that I published. But while I was in IIT Kanpur, I think I played around, and even with some of my classmates, we worked out a few different things. But it was, I guess, in my PhD that I really sort of embarked on a research problem, which led to my first paper, first published paper, which was written with my advisor. So that was just the two of us, but it was a very intense experience and very, and then I think that gave that PhD training at a place like Princeton gave me the idea of what it means to function at the frontiers of physics and how people think in trying to push ideas at the frontier. So that how to look for questions, how to pose questions, which other, I mean, there are many questions one can pose, which are the ones which are potentially doable, which are things you can immediately address, which are the ones that maybe require longer time to address, and so on. And you get a sense for all these things in your PhD period, which I think therefore it's important to do one's PhD in a place and with an advisor who can sort of guide you through this. It's a very different, it's a transition from being a student where you're trying to absorb knowledge that's already been generated and everything, and now you have to participate in the process of generating knowledge and use and sort of develop your own scientific personality or character.
I see. So I do want to come back to what you said about reinventing the wheel later. But can you explain some of your research interests right now?
So one of the main things I have been, I mean, my research interests have sort of have of course evolved, but there has been some common themes throughout. And one of the things, at least for the last 20 years or more, has been understanding this remarkable ADS CFT correspondence, which actually was discovered by one of my classmates at Princeton, Juan Maldacena. We were classmates together, and so in fact, I think I was one of the first persons he discussed this idea with also when he first had it in 1998. And that fitted in with some of the things that I was exploring as for my thesis, my PhD thesis and so on. But of course, it sort of opened up a whole new horizon, which I think string theory has been developing for the last 20 odd years. And it is something, like I mentioned earlier, this is what was very remarkable, rich about it is the fact that it relates something called quantum field theory, which is the framework that describes most of our fundamental interactions of nature, apart from gravity, and in fact also describes many strongly interacting systems in nature, even in condensed matter physics and so on. So quantum field theory has sort of been one of the pillars of 20th century theoretical physics. sort of the culmination of quantum mechanics. The understanding of quantum mechanics is sort of quantum field theory is the broad framework that sort of puts that together. So the ADS-CFT correspondence in a way relates that to something else, which is the other pillar of 20th century theoretical physics, which is general relativity, which is a classical theory, but describes gravity and is very successful at describing the universe at the very large scales, at the largest scales. It's the basis of all cosmology, gravitational waves, everything comes out of the framework of general relativity. And now this ADS-CFT tells you that there's some very remarkable counterintuitive relation between these two. I mean, counterintuitive if you haven't seen it before or thought about it, but which brings together various of the hints that people had earlier, like Hawking's work suggested and so on, but it sort of brings it together into a kind of a very remarkable statement, which is still, it's something that arose from string theory, and that's how Maldacena came up with it, but we still don't really understand why it works, or what is really behind this connection, which I think would shed a lot of light on string theory and gravity and quantum mechanics and the relation between all these three things. And so it has been my long-standing pursuit to sort of derive this duality in some physical way, which sort of makes it manifest that there is this connection. So a lot of my work has been sort of putting together the pieces for deriving this, and I think I have made some degree of progress towards it, but I think it's like, I like to think of it as one of these 1,000 or 2,000 piece jigsaw puzzle, which you have to sort of spend maybe months doing, in that case months doing, but here probably take years sort of completing to so that one sees the whole picture. So that's been one of my long-term goals, and many of the other things I've done have often been sort of spin-offs from that broader goal. And you mentioned topological string theory, conformal field theories, and so on. Many of these were kind of came out of this from trying to understand this, but in various special cases and in sort of toy examples, new examples of this correspondence, etc.
I see. So, in your research, you're basically trying to, like you mentioned, derive the ADS-CFT correspondence, those dualities that you mentioned, right? Is there any way you
Yes.
could talk about it at a level that our viewers would be able to comprehend it?
It's like I said, it is relating these two frameworks of quantum field theory and general relativity. But I will need to tell some aspects of both of these. But one striking thing about it is this notion that quantum gravity is holographic, namely that somehow the degree quantum gravity is somehow different from quantum electrodynamics. It's different from quantum chromodynamics. It's different from the quantum weak interaction, electroweak interaction, which are all quantum theories of various interactions. But and they are so the last three I mentioned are in the framework of quantum field theory. So this is even electrodynamics, which we understand by Maxwell's equations at the quantum level. The framework that describes it is quantum electrodynamics, which is an example of a quantum field theory. But quantum gravity seems to stand apart. And one of the features that this ADS-CFT correspondence tells you is that quantum gravity is somehow different from all these other quantum field theories. Firstly, because this is somehow to do with the quantum dynamics of space and time itself. And there seems to be a sort of a holographic nature of this, which is sort of difficult to describe. It's a bit like saying that there is the degrees of freedom in a theory of quantum gravity are much fewer than you would naively think. It's almost like like you can capture all the physics of a three-dimensional theory in terms of a sort of a two-dimensional hologram. So you are able to, you would not now normally think that you're kind of losing some information when you project a theory on two dimensions. Like when you see a movie or something, it's like a flat projection of a three-dimensional reality. It sort of misses out certain things about the depth and this thing. You lose that information, but somehow in quantum gravity, there is, you can project to one lower dimension, and that captures this degree. The dynamics of quantum gravity are best captured in terms of this one lower dimensional theory, which turns out to be a quantum field theory. So the relation between quantum gravity and quantum field theory goes through sort of a through this holographic connection, which connects it to a quantum field theory, which is one lower dimension. So it's sort of a very remarkable way. And the way this is encoded, the gravity is encoded into this boundary, into this quantum field theory, holographic quantum field theory, is very, very non-trivial. And it's still, that's the whole process of trying to unravel this connection. What is the dictionary between the things in the quantum gravity and the it's like a code one is trying to decode. It's written in a different language. You want to figure out what's that dictionary. So that's, I think, roughly what I would say at this stage. But it's something that's very fascinating, and I think it'll continue to power theoretical physics for the next couple of decades also. So
yeah, it definitely is fascinating. Yeah, so you are the director of ICTS, and I feel like it would be appropriate to ask this question to you. Why do you think the theoretical sciences are as important, if not more, than say the experimental sciences?
yeah, no, I think everything is very important. Science is an ecosystem, I like to often say. In fact, science and the technology that it spawns, the whole thing is it's like the Amazon rainforest or something. It needs a lot of different kinds of diversity of species and flora and fauna to make it rich and enable new things to come out. So I think an emphasis only on theoretical sciences, or only on experimental sciences, or only on applied sciences, or only on computational sciences, these are not healthy, because that's like that. I mean, and even not even in terms of hierarchy, even just in terms of like a scientific system in a country which emphasizes only one of these two, because what is most important are applications, and we need tomorrow we need the cure for the coronavirus, so we have to direct all our scientific resources towards discovering that, or we need to find a problem, we need to find a solution to our energy problem, so we have to devote all our scientific resources in that direction. That is very rarely a good strategy, I think. For at least for a country and for a scientific establishment in a major country to follow, it's not a good strategy, and certainly it's not something I think India should be following. I think the theoretical sciences are very important for multiple reasons, because they, firstly, I think they require relatively less resources in the first place, and therefore it is something one should encourage people who have the aptitude for those things to develop that. The theoretical sciences give a certain intellectual framework for a lot of the sciences, which helps in the progress of science. It helps to connect multiple disciplines. even some of the people often forget that the idea of the DNA and these things were actually a lot of the progress was powered by physicists and chemists who came into biology and brought with them their techniques of understanding complex molecules. And even the idea of the DNA molecule, that there could be a molecule which stores information, was in some sense due to Schrödinger, the physicist, the theoretical physicist. So theoretical sciences give you that sort of way of approaching and thinking about problems in a sufficiently abstract setting and general setting, which can give you new insights into how things might be working. And this is why I think in every country it's important to have people who are thinking about frontiers of ideas in the theoretical sciences as well. It should not be an optional extra. It is an essential ingredient. And this is one of the things I think the ICTS tries to sort of impart, that message that that strong theoretical thinking can have a disproportionate impact in a number of areas, and whether immediately or in the long term. And definitely also train a lot of people in that kind of thinking, which I think would be helpful whatever they choose to do.
Okay. So what does directing ICTS mostly entail for you?
Yeah, it takes away some of my time from my research, but in some ways I was always interested in science in a certain there was a certain unity of science that I always tried to hold on to, even when I was specializing in whatever, and it is necessary to specialize to sort of deepen your own impact. But I think one shouldn't also, in the course of specializing, lose sight of the bigger picture and the connections across different disciplines and the way ideas flow across disciplines, whether from mathematics to physics or mathematics to computer science or biology to computer science or physics to biology, whatever. So I think being heading this institution and one of our primary mandates is to organize these programs that bring together people from different scientific communities for these programs that are focused on particular research topics in the frontiers of various sciences. So I get a certain amount of intellectual satisfaction from seeing that and from trying to chart various ways in which you can bring together multiple disciplines and initiate conversations across disciplines, because things have often gotten so specialized that people, even in neighboring specialities, don't really talk to each other, don't know what they're doing, whereas there's a lot of scope for cross-pollination and fertilization of ideas across disciplines if one would sort of think a little, be willing to kind of engage, and there should be opportunities to engage. And I think the ICTS provides that platform for people to come and engage across disciplines, and I enjoy that, and I enjoy trying to sort of bring that about and create a different kind of thinking in India about also valuing excellence in these areas and creating a certain helping to create a culture whereby that sort of nurtured excellence is nurtured and attract young people to Indian institutions, so that India is also a frontier, I mean, is sort of pushing at the frontiers in the theoretical sciences or in sciences in general across the board. So one has to have that ambition, and I think ICTS, I like to think of as a catalyst which will help nurture bigger changes in the whole Indian scientific establishment. So that's the satisfaction that I get from heading the ICTS. And So that's something I'm happy to spend some of my time on.
Okay, so how can people get involved? What are some ways?
There are different roles as students, researchers. I mean, we have our own PhD program, and so we take in people for PhD programs and now we have theoretical physics, but mathematics, quantitative biology, and we hope to expand into theoretical computer science as well. So in some of these areas, I think we will be this ICTS will be an exciting place to do research in these areas. In particular, in string theory itself, we have a very strong group of researchers. Um, we also actually are engaging with undergraduate students, both through a regular summer research program, which many other institutes also have, but also for we have this long-term visiting student program, which is typically for people in their like people who have either finished their bachelor's or in their masters, sometimes the final year masters programs in India, Indian institutions. People can come and spend a year doing a research project in a research institution. So we actually have formalized this by putting out a sort of an application call every year around January or something, where people can then apply for this program and they can spend up to either a semester or 2 semesters at ICTS and do a long project. And that is a way to get undergraduates deeply kind of embedded into research in India, which often doesn't happen in many Indian undergraduate institutions. Though it is changing now, but this is a way in which I think some of the brightest undergraduates in the country can get an exposure to cutting edge research in India. So that's definitely one way. We have had, we would like to, in the future, increase our engagement with high school students and others who are thinking like you of pursuing careers in physics and sciences in general. But we haven't structured a program around it yet. But we do a lot of outreach, and we have archived a lot of material, including some excellent popular science talks. I don't know if you've seen some of our videos. We have a YouTube channel called ICTS Talks, and it has by Nobel laureates and Fields medalists and some of the top scientists across the world who have sort of given accessible introductions to these areas. So that's one way in which we hope to reach out to a lot of people. We are also planning to start, we've started in some small way, but we're planning to expand this notion of math circles that's popular in many US universities and other places around the world, which would sort of create communities of high school kids or even middle school to high school children who are interested in mathematics, give them a platform to sort of engage with mathematics, which is different from the way in which exams and other things treat mathematics. Sort of, we want to encourage a culture of open-ended problem solving and sort of more in the research mode of functioning rather than in the time-bound multiple choice question kind of format that exams typically get people to think in. So that's another. Math Circles is one of our other outreach projects by which we would like to engage with people from 9th grade onwards. And we've done it in a small way in Bangalore already, but now we are planning an online platform for that. I mean, thanks to COVID in some sense, where a lot of people have gotten used to moving to this online platform. We hope to have an online version of these math circles and sort of create a culture of mathematical exploration amongst school children.
Okay, so what are some traits that students should look out for in themselves to understand if they're fit for theoretical sciences?
firstly, I think you have to have a lot of curiosity, of course. I mean, uh, you should be having this sort of questioning ability to be asking questions, even if your teachers can't answer them or you can't answer them. Just don't get disheartened by that, but keep asking questions, and don't always even be prepared to question authority on that. And if you're not satisfied, be exploratory, I would say. That's the nature of good risk. I mean, try to figure out things that you see, uh, mm, uh, and be sort of problem solving, whether it is a maths problem or a physics problem or even a engineering problem, where even every little problem you solve gives you a new skill to, and sort of builds a little bit of your mental muscle in that direction. I would put a lot of these things as very primary. You should, of course, if you want to be a scientist, you should also have a certain stamina and staying power, which is be prepared for a lot of setbacks and frustrations and things, because that you have to be able to progress doesn't come like that. I mean, you have to sort of sweat it out, and you're often at a dead end. You're stuck. You don't know whether the question you're asking makes sense or is something you are going to be able to solve, or whether it's just you who is not smart enough. You'll never know, and no one will be able to tell you either. So you have to develop those judgments and those things. So you have to be motivated. You have to be passionate to be able to overcome the hurdles that all these things will bring in. And you shouldn't. I mean, in the school systems, often give more importance to knowledge, so to say, but knowledge is there. I mean, you don't have to sort of store everything in your head. I mean, you can access it when you want. You have to know what to do with knowledge. I mean, just having knowledge is just, it's like owning a pen or owning a paintbrush or owning a computer. If it just you can say I own this, but if you're not going to do something with it, then it doesn't, it's no good to you or to anyone else. So you have to know how to do things with that knowledge. You have to push that knowledge. You have to play with it, make it yours in some deep sense. So the kind of things that our school systems encourage, which is just sort of storing knowledge and regurgitating it in exams, I think that hardly tests whether you are capable of any kind of whether you have any talent towards creativity or being able to think out of the box and so on. So that's the unfortunate thing, I think, about our educational system, that we don't really emphasize the questioning, the curiosity, and so on so much.
Yeah. So, I mean, back when you were entering university, you aced your entrance exams, right? So, and most of these exams, they kind of test our ability to hold knowledge, as you're saying, theoretical knowledge. And since you have gone on to become a theorist, in hindsight, do you think that these exams really helped you prepare at all for a career in the theoretical sciences?
I mean, I would say that, well, I mean, I happened to do well in some exams, but I would say that was like a corollary of what I was following and doing myself. It was not something I particularly aimed for. It happened as a consequence. I mean, in class 11 and 12, I set myself an agenda, a self-study agenda of learning a certain set of topics in mathematics and physics. And which didn't always coincide with the syllabus for your school, and which or for the IIT exams. I mean, I was studying also partial derivatives and things which would never come in an IIT. I was not part of IIT syllabus or anything like that, or even reading a little bit of quantum mechanics and so on. But I set myself a certain agenda, and I worked through a lot of problems for testing my own understanding, and I always enjoyed that, solving problems, whether in mathematics or physics. So I guess I didn't give too many exams. I gave one or two, but I think those problem solving skills happened to come in useful for those exams. But I didn't go for any coaching classes or any of the usual stuff that people do. I think that would have destroyed my brain. So I'm a little bit protective about my mental health, and I try to avoid coaching class. I mean, I somehow had the horse sense at that age to avoid coaching classes altogether. So I've never been inside one, and I'm happy I never went there. I think, but because I think the ability to solve problems helped in those exams. So to the extent I developed that ability, it helped in my exams, and of course it helped me later as a physicist. But I don't think the exams particularly helped me in any sense to be a physicist. Time-bound exams with well-defined questions are useful. I mean, firstly, the time-bound as for a science researcher isn't such a big deal. Nature is not telling you to solve this problem by within 3 hours or within the end of the year. You have to ask the question. So the talent is in asking the right questions, having the right judgment, and in that and so on. When someone gives you a set of questions to solve, you know that someone has already solved them. So that's already a psychological barrier that you have overcome, because you know a solution exists, so you just have to find it. So okay, but in the case of nature, you even that first step you haven't overcome. So you have to have a different set of skills, I think, from those that exams kind of foster.
Yeah. And so would you recommend that even while you're learning and you're consuming knowledge, that you keep sight of the things that actually matter, and not just do it for an exam? And so, like you mentioned, the exams would just follow as a kind of corollary. And so would you recommend that kind of approach for anybody who wants to enter?
I think if you have your focus on understanding the concepts well, so that you don't like have to memorize some rules or do things. You know why you're doing that, and you can you understand the underlying concepts, and you have practice in applying them to problems. I think it follows that because then you're on very strong footing, and I think that's a good strategy, even if your only goal in life is to do well in exams.
Yeah. And so I do want to come back to this thing that you said about rediscovery, reinventing the wheel. Would you say that was how you were teaching yourself, even though during those years, and that was what you were mainly, that was your technique for learning, so to say?
Yeah, partly. I mean, just play around with things and sort of push them a little bit here and there, and try to see, observe patterns, and maybe solving a particular problem gives you an idea. Oh, okay, but that worked. How general is that? Is that like very special to this, or what does that really mean? So you are thinking not only about the answer to that particular problem, but you're thinking about the problem itself as to what is it that makes it click or work, and what is it what is at the heart of the problem. I mean, why what's going on in there? You sort of have to dive into it a little and mess around with it, and sort of then you feel more comfortable with it, and But if your goal is just to get an answer and check it with an answer key and see whether it matches, then you lose sight of all that, and then you're not this thing. So some process of reinventing the wheel and so on is very good, because it sort of makes you feel that you've made it yours. It's not some foreign body that you have sort of implanted into your mind, and it's sort of sitting uncomfortably over there, not knowing where it fits in with everything else. You have to fit it in with what you know, and what you know should be an integrated whole.
Yeah, that is extremely well said. And so we are at the end of this session. So what is one final takeaway that you want the viewers to walk away from, if they remember just one thing from this entire episode?
Well, I mean, I'm sure there are different viewers that you have who might resonate with very different things, but I would generally say, to, since the audience is are young people and so on, that I think passion is very important. You have to have the strength of conviction of your passions. And I've met many people who said, well, I loved physics and maths when I was young, but somehow, I went into engineering, and then I went into management, and then I went into selling soap, and so on. But I wish I had sort of don't put yourself in that state of mind. I know this research career and so on isn't for everyone, but if you are sufficiently passionate about it, and you see yourself sort of thriving in such a environment, and with that, with the, if you like, being in the midst of ideas and abstract thoughts in some sense, I think you should follow your convictions and your passion for it, and you won't go wrong.
Yeah. So, Professor, thank you so much for joining us today for this wonderful session, and thanks to our audience for tuning in. We hope to see everyone in our future episodes.